How are you doing? Today we are in chapter three of water and wastewater laboratory techniques. And today we're talking about laboratory wear. Um, you know, when we're in the lab, we have various funnels, pipettes, and my hope is to kind of introduce you to some of the pots and pans of the laboratory that we have. And we've kind of come a long way with laboratory wear as technology has increased. And, we have more and more disposable stuff that we can use in the lab instead of having to acid clean everything. But there's still, uh, we still use a lot of glass, and glass is probably glass and plastic are probably the predominant in ceramic are the predominant types of materials you're going to deal with in the lab. Um, the book says laboratory technicians were expected to be able to make repairs to chipped or broken glassware and to fabricate simple laboratory apparatuses. I've really found in my time that if something's broke, we just pitch it. Kind of in that disposable society, whether it's good or bad. But we kind of, once it's chipped or broken, if we can't use it for some item that is, you know, not reportable to the EPA, we just kind of pitch the item. But glass is a super cooled liquid. It's not a crystalline solid that becomes strong when placed under compression. Tampering is the process of heating glass to just under the softening point, and then rapidly cooling the surface with cold air. As inside the glass cools and shrinks, the already hardened surface is compressed and strong. New glassware is slightly alkaline and should be soaked in 1% hydrochloric or nitric acid overnight and then cleaned before use. Glass is commonly cleaned with a soft brush, hot water, or non abrasive detergent. Um, when we talk about acid rinsing or glassware, so glass can be cleaned with a mild acid. For us, we used to do it under the fume hood, but now what we do is when we're done with our BOD bottles, we'll rinse them in acid in our dishwasher, and that that acid cleans those bottles, and then we do several rinses with deionized water to remove any of the mineral stains that would be on there. So acid rinsing your glassware is important, knowing what acid to use. Um, in keeping your glassware is important. I worked at a lab a long time ago, and they said one of the most important people here is the dishwasher, the glass washer, because if he's or she is not adequately sterilizing um, the glassware, we're going to get erroneous results. And so it's important to clean our glassware. Glass is on page 29. Glass is resistant to many chemicals, but not to phosphoric acid, strong alkali, substances containing ionic fluoride, such as hydrofluoric acid and potassium fluoride. So just knowing what you can use with glass and what not to use with glass. Um, on page 31, stopcocks are an integral part of a number of glassware pieces, such as burettes and separatory funnels. Um, all ball and socket joints have to be held together by clamps. So if you have a ball and socket, those have to be held by clamps. I want to highlight on page 32, glass to glass joints should always be lubricated. This prevents the glass surfaces from freezing together and aids in the formation of a leak free seal. Silicone and petroleum based lubricants are widely used when organic solvents are not used. So, knowing what um, what type of lubricant you can use or what kind of rubber gaskets are important when we talk about glassware. Beakers. Beakers come in two general types: the Griffin beaker and the Versailles beaker, both which have a spout and a molded on the rim for easy pour. Spoutless beakers are also available. The Griffin beaker is designed shorter and wider than the Versailles for the same volume. So when we look, if you flip over on page 34, you can see a Versailles beaker and a Griffin beaker. And we use these all the time in the water and wastewater industry. They're not used for precise measurement, but they are a like for running out pH or putting your ammonia standards in and use them every day and important in the laboratory. On page 34, Erlenmeyer flasks. They are general purpose containers and reactions vessels. They are available in standard and thick wall construction. The wide mouth is better for mixing and performing titrations. So you can see on page 35 an Erlenmeyer flask with screw caps. Um, Watch glasses on 36. Watch glasses are shallow, bowl-shaped circles of glass widely used as as tops for beakers so that the technicians can observe what is happening in the beaker without opening it. The main function of the watch glass is to prevent contaminants from falling into the open beaker. So, if you have a beaker there, you can put a watch glass on there and keep the sample from um, any type of contamination. Glass bottles, we use glass bottles all the time, are used to hold samples, reagents, solutions for storage, and to perform bacterial tests on samples of 100 milliliters or more. We use glass bottles if we're going to make up a solution and we're going to keep that solution for a couple of days. We can put that in a glass bottle, label it. If it's ammonia standard 1.0, label, when it was made, and it's stored in that glass bottle, and that glass bottle could be either stored in a refrigerated environment or a non-refrigerated environment, depending on what your reagent is called for storing. Um, Many solvents and concentrated acids are packaged in a 4L screw cap glass jug by suppliers. So knowing what your supplier is providing with you. Vacuum flasks are also known as filtering flasks. These are heavy air mile style flasks with a sidearm and a neck for attachment to a vacuum source. So, on page 38 is a vacuum flask with a sidearm. And, we use these for solids. So there is a disc that sits on top of that. On the side, you can put a rubber hose that's connected to a vacuum pump, and we can draw those the solids through our either fritted glass or paper filter. Kindle flask are thick, round bottom flask with a long neck used for Kindle digestion procedure for total organic content. You can see one of those on page 39. I've never personally used one of those. We send our lab or our stuff away to a contract lab, and that's kind of higher end laboratory where maybe if you work for a bigger city, you have one of those. But in the smaller cities, we really don't get into you know, Kindle, digestion. Um, There are various others. Let's talk about the powder funnel. So when you're in a wastewater laboratory, obviously there's the powder funnel, and it's got a bigger opening so that powder can freely fall through that. and not get clogged. And they also um, can you can have a plain long sleeve filtering funnel. So it's really, what application you're using to, the funnel is just like when you're mowing grass. You don't want to spill gas everywhere. It's the same concept in the laboratory. We don't want reagents, even though we're wearing gloves, we don't want to spill extra reagents on the counter or when we're transferring liquids. We don't want those liquids to spread out. Even though we're wiping them up, uh, a good laboratory technician is clean. The guy I work with, they're really good at keeping the lab clean, and that goes a long way in the success of a lab. Uh, so on page 444, there's a perforated funnel with a vacuum attachment. So it can stand as itself, or you can put you can see the porcelain buttonhole funnel there. There's a piece of paper that will lay on the top of that, and you will pour the water or the mixed liquor or the solids in the top, and then that vacuum attachment's going to suck the water out of the sample, and so it's going to speed up the gravity process. Um, of the filtration method, because we want to know what are those solids in there. We don't want the liquid, so we want that liquid solid separation, and having a vacuum attachment and a perforated funnel is how we do that. So we pour the uh, our known sample in, and as we put vacuum pressure upon it, it's going to suck that through. And then it's going to leave the residual either on the perforated funnel, or if we put a piece of paper right there. Um, you know, Once you suck that through, we always want to spray the sides of that off so that the solids will lie back down on the paper, especially if we're using a paper filter. Sometimes we don't use the a paper filter. Sometimes we just use the funnel itself with the fritted glass because of acid. So acid will eat the paper. On page 47, we have a separatory funnel. We want to, like when we make polyseed, we'll bubble polyseed. And what we do is we put a seed packet in there. It is a solid substance. The air, we aerate it for an hour. And when we aerate it, it breaks that solid substance up into a seed concentration that's our in the jar. And then we'll put that in a separatory funnel because we want the solid chunks to settle to the bottom and the floatables to float to the top. And so it's basically acting as a clarifier. And the reason why we want that is we want a continuous mix of solids. And when we pipette, we don't want a big chunk. We want a well mixed, well dissolved seed. And so we'll use a separatory funnel just to allow that gravity filtration or gravity to happen. There's some, liquid, heavier than water, continuous liquid extractors on page 48, and then lighter than water, continuous liquid extractors on page 49. Once again, those are probably something that you only use in a bigger city and a bigger laboratory. On page 50, ceramic or porcelain materials are used whenever high temperatures are required in the procedure and the chemical resistance similar to that of glass is needed. Ceramics are made from clays and molded when wet into a desired shape, allowing them to dry, glazed, and then fired at higher temperatures. So a lot of times we'll use these in the lab when we were trying to do volatile solids. If we are putting those into an oven and hitting them with 550 degrees so that we can see what volatile solids are going to separate from the solids. So we'll put mixed liquor in there or something from our sludge sample in there, and we'll dry it. And so you'll get a cake formation there on those ceramic, and then we will fire that in a muffle furnace. And we use the ceramics because they're really resistant to the high temperature. And so in the laboratory, you'll use a lot of those type ceramics in our day-to-day use. Plastic and you know we use a lot of synthetic plastics in the lab. Um, they come in a wide variety. Some are disposables. Um, it says on page 52, except for fluorocarbon resins, most plastics cannot be used above 100 C. So a lot of times we don't put high heat to plastics, and we use them a lot in squeeze bottles, beakers, pipettes, and some of those plastics are disposables and some are clean. One great thing about it is some of them don't don't get moldy as others. And the thing I like about it is plastics are hard to break. And so for me, I'm klutzy, so having plastics that don't break are awesome. They can be chemical resistant group of resins, and on page 54, and you can see all the polys. It lists all the polys. Um, but polycarbons are rigid, tough, and crystal clear, and they make ideal material for safety glasses and blast shields. Mhm. On page 56 is a wash bottle. Wash bottles, if you're going to wash off your DO probe, you would use a wash bottle to spray the edge of the DO probe off, or a pH probe. We every time we use our probe, we want to wash it off and make sure that we're not doing contamination. Page 57, gloves are used in the laboratory to protect the technician's hands. We always want to wear the right gloves. If we are working with heavy acids, we don't want to use a rubber glove, a heavy rubber glove that's made for that. Plastic gloves, if we are working with a sample that possibly could have, or vinyl, plastic or vinyl gloves, um, used for the recommended use, whether that be contamination or protecting yourself from bacterial, um, infection. Disposable pipettes are frequently used in the microbiological laboratory. Um, so you can kind of see some disposable pipette tips. We use those on um, your automatic pipetter. On the top of page 59 is some serological pipettes. Tubing, a lot of times we have tubing in the laboratory. Um, Latex and natural rubber tubing has been used for 100 more years. All your vacuum pumps use some sort of tubing, and then you can have fittings. That way you can join several vacuum pumps together, or have valves. So just knowing that if it somewhere someone has done it before, and so there's Y connections and ways, that way you don't have to continually pull a tube off from one vacuum flask to another. Um, It says sample containers are largely overlooked part of the laboratory analysis. Technicians commonly grab any available container and go get a sample. However, more than 50% of all analytical problems actually arise during the sampling process. The good may relate to the container used for the sample. The ideal container is inert to the sample, easily clean and unbreakable and inexpensive. Um, you know, just knowing that the way you sample and how you sample is is just as important as the reading the results or performing the test. You know, you can have contamination or a mix up from improper sampling that will affect the results. And a lot of times, especially if you're working with pre-treatment and you're taking a sample that these people are getting charged off of, you know, we want to have a good moral conscious about what we sampled and making sure that we cleaned it from the industry that we used before, whether that be our tubes from our samplers all the way to our um, sampling containers. On 337, that's a pre-sterilized sample container with decor tablets. So you could use that for grabbing a E. coli sample. And the reason why you can see there's a little ball of decor tablet in there is because we want to freeze that sample from any chlorine. So when we grab a E. coli or a fecal, we want to freeze it as it is in the sample. There's a reusable filtration unit, page 65. Metalware, we use you'll come into stainless steel. It's stainless steel is compression. Uh, it can be used in compression, but there also is corrosion resistant. On page 666 is a hand operated vacuum pump. You know, that would be connected to a vacuum flask, and as you pump the pump, that's going to create that vacuum pressure. It's a little bit cheaper of a way to create that vacuum other than having a vacuum pump. And you can do it on site because maybe perhaps that you don't have access to a vacuum pump. Well, that is it for chapter 3. I hope you enjoyed it. Thank you.